Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also hit the bell icon to get notified of new videos. Today we will be diving into the fascinating world of blockchain cryptography math, but don't worry, we're going to explain everything in plain English. Cryptography might sound intimidating, but it is at its core, it's just clever math that keeps your digital assets safe. Think of blockchain cryptography as the digital equivalent of a high-tech vault that uses mathematical locks instead of physical ones. In this presentation, we will explore how blockchains use cryptographic principles to create an immutable, secure, and transparent ledger. We will break down complex concepts like hash functions, public key cryptography, digital signatures, and Merkle trees into bite-sized, understandable pieces. By the end of this session, you will understand why blockchain is considered one of the most secure technology ever invented and how mathematical principles make it virtually impossible to tamper with any recorded transactions. Whether you are interested in cryptocurrency, distributed system, or just curious about how this revolutionary technology works under the hood, this presentation will give you the foundation knowledge you need. What is cryptography? Before we jump into blockchain-specific cryptography, let's establish what cryptography actually is. At its most basic level, cryptography is the science of securing information by transforming it into an unreadable format that can only be converted back to a readable format by someone who has the correct key. The word cryptography comes from Greek word meaning hidden writing. Throughout history, humans have used cryptography to send secret messages, from Julius Caesar's simple letter shifting cipher to the complex Enigma machine used in World War II. In the digital age, cryptography has become exponentially more sophisticated and essential. Every time you visit a secure website, send an encrypted message, or make an online payment, cryptography is working behind the scenes to protect your data. Modern cryptography relies on mathematical functions that are easy to compute in one direction, but practically impossible to reverse without proper key. This asymmetry is what makes cryptography so powerful. In blockchain technology, cryptography serves three critical purposes. It verifies identity of users, ensures data integrity, and maintains the privacy of transactions. The mathematical foundations are complex, but the practical applications are elegant and intuitive once you understand the basic principles. The basically you have securing the information throughout mathematical transformation. You run the plain text and use a key and run through an encrypted function. This encrypted function produces something called ciphertext, and the only way they can reverse back that encryption is by having the decryption key and then going through doing the reverse of the encryption to recover back the plain text. Let's start with one of the most important cryptography tools in blockchain, the hash function. A hash function is like a mathematical meat grinder. You put data in and it produces a fixed size output called hash or digest. No matter how much data you feed into a hash function, whether it's a single word or an entire library of books, the output is always the same. For example, the SHA-256 hash function with Bitcoin, which is used by Bitcoin, always produces a 256-bit output, which is typically represented as a 64 characters hexadecimal string. What makes the hash functions special are their unique properties. First, they are deterministics. The same input always produces the same output. Second, they are one-way functions. You cannot reverse engineer the original input from the hash. Third, they are collision resistant. It's virtually impossible to find two different inputs that produce the same hash. Fourth, even a tiny change in the input creates a completely different hash known as, this is known as the avalanche effect. In blockchain, every block contains a hash of all the data in that block, and this hash becomes part of the next block, creating an unbreakable chain. If someone tries to alter data in one block, the hash changes, breaking the chain and alerting everyone to the tampering attempt. This is why blockchain is considered immutable. You know, the hash function, any size, you can put any size and get SHA-256, for example. It produces a fixed 256-bit output, and this is basically the block hash. Let's dive deeper into the specific properties that make hash functions so crucial for blockchain security. The deterministics property means if you hash the phrase "hello world" with SHA-256, you always get the same 64-character hexadecimal string, no matter when or where you compute it. This predictability is essential for verification. Anyone can independently verify that the piece of data produces a specific hash. The one-way property, also called pre-image resistance, means it's computationally infeasible to determine what input created a given hash. If I give you a hash, you cannot work backwards to figure out what the original message was. The collision resistance property means it's virtually impossible to find two different inputs that produce the same hash output. With SHA-256, there are 2 to the power of 256 possible hash values. That is more than the number of atoms in the observable universe. The avalanche effect means that changing even a single character in the input produces a completely different hash. If you hash hello world and then hash hello world with exclamation, with just the exclamation point added, the resulting hashes look completely unrelated. These properties combined make hash functions perfect for ensuring data integrity in blockchain. Now let's explore public key cryptography, also known as asymmetric cryptography, which is the second pillar of blockchain security. Unlike traditional symmetric encryption, where the same key is used to encrypt and decrypt, public key cryptography uses a pair of mathematically related keys, a public key and a private key. Think of it like a mailbox. Anyone can drop a mail into your mailbox using your address, your public key, but only you have the key to open it and retrieve the mail, which is basically the private key. In blockchain, your public key serves as your address, where others can send you cryptocurrency or data. Your private key is what allows you to access and spend those funds or prove ownership of assets. The mathematical relationship between these keys is based on complex number theory, specifically involving problems like elliptic curve mathematics or large prime numbers factorization, which are easy to compute in one direction but extremely difficult to reverse. For example, multiplying two large prime numbers is easy, but factoring the result back into those primes is so computationally intensive that it would take more even the world's most powerful supercomputer millions of years to solve. This mathematical asymmetry is what makes public key cryptography secure. You can freely share your public key with the world, and even if someone knows your public key, they cannot derive your private key from it. How key pairs work. Let's break down exactly how public and private key pairs function in blockchain. When you create a blockchain wallet, the software generates a private key, typically a random 256-bit number. From this private key, a corresponding public key is mathematically derived using elliptic curve multiplication, which is a one-way mathematical function. From the public key, your blockchain address is then created by applying hash functions. This creates a chain of derivation. Private key generates public key, which generates an address. The crucial point is that while you can always derive the public key from the private key, you cannot reverse the process. The private key must be kept absolutely secret because anyone who possesses it has complete control over the associated assets. Think of your private key as the password to your entire digital fortune. In contracts, your public key and address can be shared freely. They are like your account number that others need to send you funds. When someone sends you cryptocurrency, they're essentially creating a mathematical puzzle that can only be solved by someone who possesses the private key corresponding to the destination address. The transaction is broadcast to the network, included in a block, and added to the blockchain, but the funds can only be moved again by someone with a private key. This system eliminates the need for trusted intermediary like banks because the math itself enforces ownership and authenticity. Digital signatures are where hash functions and public key cryptography come together to create one of the most powerful security mechanisms in blockchain. A digital signature serves the same purpose as a handwritten signature. It proves that a specific person authorized a specific document or transaction, but it's far more secure and impossible to forge. Here is how it works in blockchain. When you want to send cryptocurrency or execute a transaction, you use your private key to create a digital signature for that transaction. The process involves taking a hash of the transaction data and then encrypting that hash with your private key using a mathematical algorithm. This signature is unique to both the transaction and your private key. You then broadcast the transaction along with your signature and public key to the blockchain network. Other participants can use your public key to decrypt the signature and compare it to a hash they compute from the transaction data. If they match, it proves two things. First, that the transaction definitely came from the owner of the private key. And second, that the transaction hasn't been altered since it was signed. Even a tiny change to the transaction would result in a different hash and the signature wouldn't verify. This mathematical proof of authenticity is more reliable than any physical signature because it's based on cryptographic certainty rather than human judgment. No one can forge your digital signature without your private key, and in any attempt to modify the signed transaction will be immediately detected. We here see the transaction data. You compute the hash and the transaction hash is signed by the private key. Signed with the private key, create the digital signature. Your public key decrypt with your public key, and they compare the hash and validate if match. Verification process basically will verify your transaction from your public key and basically compare the hash to validate that the transaction matches. Let's walk through the complete digital signature verification process step by step, really to understand how the math ensures security. Imagine Alice wants to send 5 bitcoins to Bob. First, Alice wallet software creates the transaction data, which includes information like the amount, Bob's address, and reference to previous transactions where Alice received the funds. The wallet then computes a hash of this transaction data using SHA-256. Next, Alice's wallet takes this hash and encrypts it using her private key through an algorithm like ECDSA, which stands for elliptic curve digital signature algorithm. This produces the digital signature. Alice's wallet then broadcasts the transaction, the signature, and her public key to the blockchain network. When network nodes receive the broadcast, they perform the verification process. They take Alice's public key and use it to decrypt the signature, which should produce the original hash if the signature is valid. Simultaneously, they independently compute a hash of transaction data. If the decrypted hash from the signature matches the hash they computed from the transaction data, the signature is valid. This proves that someone with Alice's private key signed that exact transaction and the transaction hasn't been modified. The beauty of this system is that verification requires only public information, the transaction data, the signature, and the public key. Yet creating the signature requires the private key, which only Alice possesses it. This asymmetry enables trustless verification, a cornerstone of blockchain technology. Now let's explore another brilliant cryptographic structure used in blockchain, the Merkle trees. Merkle, named after computer scientist Ralph Merkle, who patented the concept in 1979. A Merkle tree is a data structure that allows efficient and secure verification of large data sets. Think of it as a tree built from hashes, where each leaf node represents the hash of a transaction, and each non-leaf node represents the hash of the shard node, all the way up to a single hash at the top called the Merkle root. In blockchain, each block contains potentially thousands of transactions. Rather than storing every transaction hash in the block headers, blocks only store the Merkle root. This single hash represents all transactions in the block in a compact, verifiable way. The elegance of Merkle tree lies in the efficiency. If you want to prove that a specific transaction is included in a block, you don't need to provide all the transactions, you only need to provide the transaction itself, the Merkle root, and an algorithm number of intermediate hashes called the Merkle proof or Merkle path. For example, in a block with 1000 transactions, you only need about 10 hashes to prove inclusion rather than all 1000. This makes verification incredibly efficient, which is crucial for lightweight clients like mobile wallets that don't download the entire blocks. The Merkle tree structure also preserves the integrity guarantee. If any transaction changes, its hash changes, which changes its parent hash, and so on up the tree, ultimately changing the Merkle root. Let's walk through exactly how a Merkle tree is constructed and used in blockchain. Imagine a block contains 8 transactions, which we will call transaction A through H. First, each transaction is hashed individually. So we hash transaction A to get hash A, hash transaction B to get hash B, and so on through hash H. These are our leaf nodes at the bottom of the tree. Next, we pair up these hashes and hash the pairs together. We concatenate hash A and hash B together. then hash the result to get hash AB. We do the same with hash C and hash D to get hash CD. Same with E and F. Now we're at the second level with 4 hashes. We repeat the process, concatenate and hash AB and hash CD, get hash ABCD and concatenate and hash EF and hash GH to get EFGH. Now we have 2 hashes at the third level. Finally, we concatenate the hashes these two produces to the Merkle to produce the Merkle root hash ABCDEFGH. This single hash is stored in a block header. Now suppose you want to prove the transaction C is in the block. You provide transaction C itself and the Merkle root, which would consist of hash D, hash AB, and hash EFGH. The verifier can then hash transaction C to get hash C, concatenated with hash D, and hash to get the hash CD, concatenate that with hash AB, and hash to get ABCD, then concatenate with hash EFGH and hash to get the Merkle root. If this matches the Merkle root in the block header, transaction C is proven to be in the block. Now let's discuss proof of work, which is the cryptographic puzzle that makes blockchain secure against attacks. Proof of work is the consensus mechanism used by Bitcoin and some other blockchains to determine which participant gets to add the next block to the chain. The concept is ingeniously simple yet incredibly powerful. When miners want to add a new block, they must solve a computational puzzle that requires performing trillions of hash calculations. The puzzle is this: find a number called a nonce, which when added to the block data and hashed, produces a hash with a certain number of leading zeros. The number of required leading zeros determine the difficulty. For example, Bitcoin might require a hash that starts with 19 zeros, which means you need to find a hash that's less than a very small target number. The only way to find such a hash is through the brute force, trying different nonce values until you get lucky. On average, miners must compute billions or trillions of hashes before they find a valid one. This requires massive computational power and electricity, which is why it's called proof of work. You're proving you did the computational work. Once a miner finds a valid nonce, they broadcast the block to the network. Other nodes can quickly verify the solution by performing a single hash calculation. This asymmetry, which is hard to find, easy to verify, is crucial. The difficulty of the puzzle makes it economically infeasible to attack the blockchain because you'd need to control more computational power than all honest miners combined. The proof of work difficulty is what makes blockchain practically immutable. Let's understand why through some numbers. In Bitcoin, a new block is mined approximately every 10 minutes. The network automatically adjusts the difficulty every 2016 blocks to maintain this rate regardless of how much total mining power is active. As of recent years, the Bitcoin network hash rate exceeds 400 exahashes per second. That's 400 quintillion hash calculation every second. To put this into perspective, if you wanted to attack the Bitcoin blockchain and rewrite history, you'd need to redo the proof of work for the block you want to change and all subsequent blocks, and do it faster than the rest of the network of the network is adding new blocks. With the current difficulty and hash rate, this would require controlling more than half of the network's computing power, an attack scenario known as 51% attack. The deeper a block is in the blockchain, the more secure it becomes because you need to redo more and more work. A transaction that's 6 blocks deep, which Bitcoin considered reasonably final, would require redoing the work of all 6 blocks, plus keeping pace with the new blocks being added. The computational cost on electricity required to make such an attack economically is making it's basically irrational for Bitcoin. The security comes from the sheer scale of honest mining power. This is why proof of work is sometimes called one CPU, one vote. The more computational power you contribute, the more say you have in the consensus, and economic incentives align participants trends towards honest behavior. Let's examine how all these cryptographic components fit together in the actual blockchain data structure. A blockchain is literally a chain of blocks, where each block contains three main parts: the block header, the transaction data, and the Merkle tree structure we discussed earlier. The block header is the most crucial part for maintaining the chain's integrity. It contains several key pieces of information. First, there is the version number, which indicates which protocol rules the block follows. Second is the hash of the previous block's header, which is what creates the chain linkage. Third is the Merkle root, which represents all transactions in the block. Fourth is the timestamp indicating when the block was mined. Fifth is the difficulty target, which specifies how hard the proof of work puzzle was. And finally, there is the nonce, which is the solution to the proof of work puzzle. When a new block is mined, its header includes the hash of the previous block. This creates an unbreakable backward link. If someone tries to alter a transaction in an old block, the Merkle root changes, which changes the block's hash, which breaks the link to the next block. To fix the link, you would need to recalculate the hash, which means finding a new nonce, which requires redoing the proof of work. Then the next block's link would be broken, requiring you to redo its proof of work, and so on for all subsequent blocks. This cumulative proof of work creates a computational barrier that makes the blockchain effectively immutable. When a new block is broadcast to the blockchain network, every node performs a series of cryptographic validations before accepting it. Understanding this validation process reveals how blockchain achieves security without central authority. First, nodes verify that the block's hash meet the difficulty target. In other words, the valid proof of work was performed. This is quick to check. Just hash the block header once and confirm it has the required number of leading zeros. Second, nodes verify the previous block hash and the header matches the hash of the latest block in their copy of the chain, ensuring the new block properly extends the chain. Third, nodes reconstruct the Merkle tree from the transactions in the block and verify that the Merkle root is in the header, confirming transaction integrity. Fourth, nodes validate every single transaction in the block. For each transaction, they verify the digital signature using the sender's public key, confirming that the transaction was authorized by the private key holder. They check that the sender actually has the funds being sent by tracing back to the blockchain to previous transactions. They verify that the same funds aren't being double spent. that these inputs haven't been used in any previous transaction. Only after all these checks pass does a node add the block to its local copy of the blockchain and relay it to other nodes. This rigorous validation process, performed independently by thousands of nodes, makes distributed consensus without any central authority. The cryptographic proofs leave no room for disagreement. One of the most elegant achievements of blockchain cryptography is solving the double spending problem, which plagued digital currency attempts before blockchain. Double spending means using the same digital money twice, like making photocopies of a dollar bill. In the physical world, when you hand someone cash, you no longer have it. The physical transfer prevents double spending, but digital information can be copied perfectly. So, how does blockchain prevent someone from sending the same Bitcoin to two different people? The solution combines several cryptographic mechanisms. First, every transaction references specific previous transaction output as its input. When you receive Bitcoin, it's locked to your public key. To spend it, you must reference that specific transaction output and provide a digital signature proving you own the private key. Once the output is spent, it's marked as spent on the blockchain. If someone tries to create another transaction using the same output, network nodes will reject it because they can see that output was already spent in an earlier transaction. The blockchain serves as a global ledger that everyone can verify. But what if someone tries to broadcast two conflicting transactions simultaneously to different parts of the network? This is where proof of work and consensus comes in. Eventually, both transactions will compete to be included in a block. Miners will include one or the other, but not both. Once a transaction in that block is added to the chain, the other transaction becomes invalid. The longer the chain grows beyond that block, the more final the transaction becomes. This is why Bitcoin considers transactions confirmed after six blocks. After six blocks, the probability of reversal becomes automatically small. Let's dive deeper into elliptic curve cryptography, which is the specific mathematical framework used for public key cryptography in most modern blockchains, including Bitcoin and Ethereum. Elliptic curve might sound exotic, but they are just a particular type of mathematical curve described by an equation. Bitcoin uses a curve called SecP 256K1, which looks like a smooth, symmetric curve when plotted on a graph. The equation is relatively simple: y squared equals x cubed plus 7. The cryptographic magic comes from defining mathematical operations on points on this curve. Here's the insight: if you start with a point on the curve called the generator point and add it to itself repeatedly a certain number of times, you get another point in the curve. This repeated addition is called scalar multiplication. Given the generator point and the result point, it's computationally easy to verify the relationship, but given only the 2 points, determining how many times you added the generator to itself is computationally infeasible. This is called the discrete logarithm problem. This asymmetry is perfect for cryptography. Your private key is simply a large random number, and your public key is the point you get by multiplying the generator by your private key number. Anyone can verify a relationship using your public key, but they cannot work backward to find your private key. Elliptic curve are preferred over other cryptography systems like RSA because they provide equivalent security with much smaller key sizes, making them more efficient for blockchain use. Understanding the actual security levels of blockchain cryptography helps appreciate why these systems are considered so secure. When cryptographers talk about security, they measure it in bits. A system with n bit security means an attacker would need to perform approximately 2 to the power of n operation to break it. Let's put Bitcoin numbers in perspective. Bitcoin uses 256-bit private keys, but due to the birthday paradox and specific properties of elliptic curve, the effective security is about 128 bits. This means an attacker would need to perform 2 to the power of 128 operations to crack a Bitcoin private key. How big is that number? It's approximately 340 undecillion, or 340 followed by 36 zeros. If every person on Earth had a billion computers and each computer could try a billion key per second, it would take trillions of times the age of the universe to crack a single private key. The SHA-256 hash function provides 256-bit security against pre-image attacks and 128-bit security against collision attacks. These security levels far exceed what's considered safe. For comparison, 128-bit security is considered unbreakable with current and foreseeable technology. Bitcoin 256 private keys provide a comfortable security margin even considering potential advances in computing, including quantum computers. It's worth noting that these security levels assume proper random number generation when creating a private key. If the randomness is weak or predictable, security can be compromised regardless of the mathematical strength of the algorithm. The future threat of quantum computers to blockchain cryptography is a topic of significant discussion in the cryptography community. Quantum computers leverage quantum mechanical phenomena to perform certain calculations exponentially faster than the classical computers. Two quantum algorithms practically concern cryptography: Shor's algorithm and Grover's algorithm. Shor's algorithm can break public key cryptography, including elliptic curve cryptography in polynomial time, meaning it's sufficiently powerful quantum computer could derive a private key from a public key. Grover's algorithm can speed up brute force attacks on symmetric encryption and hash functions, effectively having their current security levels. For blockchain, this means SHA-256 would go from 256-bit to 128-bit security, which is still considered secure. However, the elliptic curve cryptography used for digital signatures will be vulnerable. The good news is that sufficiently powerful quantum computers don't exist yet, and likely won't be for years or decades. Quantum computers powerful enough to threaten current blockchain cryptography would need millions of high-quality qubits, while today's quantum computers have only dozens to hundreds of noisy qubits. Additionally, blockchain can be upgraded with quantum-resistant cryptography. Post-quantum cryptographic algorithms already exist based on mathematical problems that even quantum computers can solve efficiently, such as lattice-based cryptography or hash-based signatures. The transition to quantum-resistant cryptography will be complex but feasible, likely happening gradually as quantum computing processes. Understanding the theory is important, but let's discuss practical security considerations for anyone using blockchain technology. The cryptographic algorithms in blockchain are extremely secure, but the weakest link is often human behavior and operational security. First and foremost, protecting your private keys is absolutely critical. Never share your private key with anyone. Never store it in plain text on a computer connected to the internet, and never enter it on a website. Use hardware wallets for significant holdings. These devices keep private keys isolated from internet connected computers. When creating a wallet, ensure you're using software from a trusted source, as malicious wallet software could generate weak keys or steal your existing ones. Always verify addresses carefully before sending transactions because blockchain transactions are irreversible. One wrong character in an address means your funds are sent to the wrong place permanently. Use address checksum when available. These are built-in error detection codes that help catch typos. For exchanges and services, enable two-factor authentication and use unique, strong passwords. Be aware of phishing attacks where scammers try to trick you into revealing private keys or sending funds to malicious addresses. When backing up wallet seeds or private keys, use multiple physical backups in secure locations. Consider metal backup plates that can survive fires and floods. Never store backup digitally unless encrypted properly. Remember that blockchain transactions are pseudo-anonymous or not anonymous. Your transactions are publicly visible, so consider privacy implications. The math makes blockchain secure, but operational security is your responsibility. As we conclude this exploration of blockchain cryptography, let's reflect on what makes this technology revolutionary. Blockchain combines multiple cryptographic primitives, which like hash functions, public key cryptography, digital signature, and Merkle trees, into an elegant system that achieves something previously thought impossible, which is maintain a consistent tamper-proof ledger across a distributed network without any central authority. The mathematical certainty provided by cryptography replaces the need for trust in institutions. You don't need to trust a bank, government, or company. You can verify everything yourself using cryptographic proofs embedded in the blockchain. This trustless nature is blockchain's superpower. The immutability created by chaining cryptographic hashes makes blockchain an ideal technology not just for cryptocurrency, but for any application requiring an auditable permanent record, supply chain tracking, medical records, property titles, voting systems, and more. As blockchain technology matures, we'll likely see improvements in efficiency, privacy features like zero knowledge proofs that allow proving facts without revealing data, and eventually quantum resistant cryptography. The fundamental cryptographic principles we've discussed will remain relevant because they are based on deep mathematical truth. Whether blockchain ultimately revolutionizes finance, governance, or other sectors, understand its cryptographic foundation helps you appreciate both its possibilities and its limitation. The math doesn't lie, doesn't forget, and can't be corrupted. That's the promise of blockchain cryptocurrency. Thank you for your attendance. Please consider subscribing to the channel.